Hello everybody, today we will tune PID controller using a modified gradient-based optimizer sine cosine algorithm for Quad-rotor. I am Mohamed Ibrahim Zineldin, Mechatronics student at Faculty of Engineering, Menoufia University. For this session, we will have a look of our dynamic model for UAV system, then we will analyze it, presenting the design of our control system and the required trajectory. Afterwards, we will discuss PID controller and how it works, defining the objective function for PID tuning optimization problem. Therefore, we will discuss gradient-based optimizer and will propose the gradient-based optimizer sine cosine algorithm. Finally, we will have a look of our Simulink model and MATLAB code. As shown in the figure, the structure of quad-rotor helps it to start to fly in the air. When all four rotors rotate in the same directions, then vertical upward lift force produced, and the quad-rotor can fly. By changing the speed of these rotors, the quad-rotor can move in pitch, roll, yaw, hover, take off, and landing positions. The dynamic model can be formulated as follows, describing the translation movements x, y, and z, and the rotational movements roll, pitch, yaw. To make it easy for control, we will linearize the system around the point of hovering, resulting these equations, which enables us to get transfer function easily by applying Laplace transform. To design our control system, we should identify degree of freedoms and the controller signals. The controller signal U1 for Z plant, which is in the first feedback loop, and the controller signal U2 for cascaded couple system Y plant and phi plant, where second loop for phi and the third loop for y. In this work, the required trajectory is described by equation of reference 1 and equation of reference 2. To achieve this path, we use PID controller. We can observe the effect of each PID gains on the system from the response curve. The PID controller is used to minimize the tracking error by proportional gain, which reduces the rise time, and the integral gain, which eliminates the accumulative steady-state error by integration, and the derivative gain, which overcomes the overshoot and makes the system damp because of derivative. So the PID output is a summation of proportional and integral and derivative terms. To formulate PID tuning as optimization problem, we should identify objective function, which is combined of integral absolute error, and the integral squared error, and the integral time-weighted absolute error, where the solution is the KB, KI, and KD parameters. To solve this problem, we will use Metaheuristic path. We modified gradient-based optimizer algorithm proposed by Iman Ahmadi Nifar and inspired by gradient-based Newton's method, which uses two main operators, gradient search rule and the local escaping operator. We discovered that applying sine and cosine terms to equation 6 enhances the exploration ability, which makes the convergence more faster, and it reaches optima in less iterations. In this slide, you can see the pseudocode of the proposed GBO-SCA algorithm. And here are some convergence curves for some benchmarks functions. Finally, we will discover the Simulink model and MATLAB code. Here is the Simulink model. As we defined in our linearized system, we can find the z value from double integration of z double dot. In the same way, we can find the phi angle. So we can find the value of y. To tune PID for each degree of freedom, we separated them into other Simulink files. And use the step unit as our test function. Then we programmed our objective function and upper and lower bounds for each plant. After that, we implemented GBO-SCA tuner for each plant. To obtain the overall tuned system, we defined the number of search agents and maximum iterations of GBO-SCA algorithm. Then we can run this script. It takes some time. Finally, we can find the wave of the control Z and the controlled phi and the controlled y. To investigate the properties of the controlled systems, we have built this model and the phi Karak model. Then we can run this script and here we can check the rise time, settling time, and overshoot, undershoot, peak, and peak time for each Z and Y and phi. Eventually, I would like to thank you for your time and consideration.